In this video, we're going to continue section 2.2 with conditional statements. So conditional statements are statements in this form. If something happens, then something will follow. That is a conditional statement. So the if is what we would call the hypothesis. Then would be the conclusion. So an example, if you play well in soccer practice, then you will start in the game. Having trouble running those words together, sorry. In the game. Okay, so that's an if-then statement. I'm going to draw this as a Venn diagram. So what we have is the idea that if our premise happens, right, if our hypothesis happens, then a conclusion is going to happen. And the idea is you would expect the conclusion to follow once the hypothesis happens. You would expect that to occur. So what we expect to happen is that if our hypothesis happens, in this case, you play well, then you would expect to follow from that you start in the game. And I'll just put start in the game. Okay, so start. So it's basically a subset relationship. That's the idea. If an if-then statement is issued, something happens, something's going to follow. This occurrence, something happening, lands it firmly in the following conclusion, okay? And that's how we kind of present if-then statements in a Venn diagram. So we'll look more at that as we kind of start coming back to arguments. Before we do that, though, I want to kind of practice putting statements into the if-then format. So we're going to actually, I'm going to refer to your book for this so that we're not writing a bunch of stuff down and wasting a lot of time. If you go to your book, and you may want to pause the video, turn to page 74. I'd like you to look at number 3. So I'm going to read the statements, but I'm not going to write them. And what we're going to do is put these statements into the if-then format, okay? So if you want to read along with me, pause, and here we go. So part A says, taking a hard line with a bill collector may lead to a lawsuit. So if we want to put that into an if-then statement, what we would say is, if a person takes a hard line with a bill collector, it's going to follow. So here's the conclusion. Then it may lead to a lawsuit. So that's how we could write this in an if-then format. And I do want to point out that in the formatting of this, the fact that they use the word may kind of allows for some wiggle room in the conclusion. That happens a lot when people are debating. But that's how we could state it in an if-then format. Okay, let's try part B. All employees in the TriPack company must retire by age 65. Okay, so in an if-then format, what we're saying is that if someone is an employee, if a person is an employee of the Tripet Company, then they must retire at 65. All right, so that's the if-then format. Okay, so let's try part C, and maybe you try to word it into the if-then format. I'll read it, and if you pause and try to word it yourself and see if we kind of came up with something similar. So if a class, oh, I'm sorry, there must be, wow, I'm like giving it away. There must be a 2-hour session if the class is to meet only once a week. Okay, so go ahead, pause the video, try it. But thankfully, this one kind of sets it up for us a little bit because it has the if in there. So if the class meets twice a week, if that occurs, then it will be in a 2-hour format. And if you struggle with this, kind of think about which one is the subset. Which one, if it happens, is going to have the other one follow. That's kind of how you determine which is the if and which is the then. So the conclusion is always the bigger category, the thing that has to follow from the other one occurring. Okay. Let's go ahead and kind of go into these conditional statements a little bit more. Every conditional statement has 3 related statements. So from that one statement, we actually have 3 statements that are related to that statement. I'm going to kind of spell related a little better because that just like looked really hard to read. There we go. Okay. So the first is the statement itself. And I'm going to write it in this general format of if P, then Q. So whatever P is, if the class meets twice a week, then Q would be the 2-hour format. Okay, great. Here's the other 3 statements that are going to follow immediately from that statement. There's the converse of this statement. The converse is if Q, then P. So we could say, if you're kind of looking at the statement above that I have part C here, if the class meets twice a week, then it will be in a 2-hour format. The converse of that would be if a class is in the 2-hour format, then the class meets twice a week. The question is it always true, the converse? And the answer is not necessarily. No, not necessarily. Let's look at the inverse of the statement. If not P, does it follow? Then not Q. And sometimes it follows. Sometimes it doesn't. The last one is called the contrapositive. Contrapositive is like the converse of the statement, except it's of the inverse. So if not Q, then not P. And here's what's interesting. These two, the statement and the contrapositive, are what we call logically equivalent, meaning they actually, if the statement happens, the contrapositive happens. It is a true statement. And we'll talk about why in just a second, okay? But let's look at some examples of how the converse, inverse, and contrapositive get worded specifically, okay? Again, go ahead and grab your book. I want to look at page 74, number 10 this time. Okay, so I'm going to read the statement, but then we're going to write the converse, inverse, and contrapositive of it. So the original statement was, if the weather is fair, the opera will be sold out. Okay, So let's write the converse of that statement. So the converse is taking the conclusion first. So if the opera is sold out, sorry about my dog. If the opera is sold out, then the weather is fair. Okay, the inverse of this statement. If the weather is not fair, so we're taking the negative of the hypothesis. So if the weather is not fair, then the opera will not be sold out. And then last, we have the contrapositive. So this starts with negating the conclusion. Okay, so the conclusion. If the opera is not sold out, then the weather isn't fair. Sorry, it's loading. There we go. The weather isn't fair. And this is actually the only one that does work for the original statement in terms of truth. The other two might be true. It could possibly be true. But this one, if you are accepting the claim that if the weather is fair, the opera is going to be sold out. Okay, like that happens when the fair weather happens, the opera sells out. Okay, if you accept that statement as true, then the contrapositive is also true, meaning if the opera is not sold out, then the weather isn't fair. And the reason is because of the way I drew the subset. Okay, so in the original, we said fair weather. Oops. Wow. I'm going to draw oblong circles to fit in here, okay? Fair weather leads to sold out opera. Okay? That's the claim. So the minute you have fair weather, you have a sold out opera. In the contrapositive, we're saying that the opera is not sold out. So now we're outside of the sold out box. Therefore, the weather is not fair. And that is a valid conclusion, assuming that the first thing is a true statement. Because we're taking ourselves outside of both circles automatically with the first statement. And therefore, it would obviously follow that the weather is not fair. Okay. So, let me mention the phrase I used earlier. The note, the original statement and contrapositive are logically equivalent. So if you assume the truth of one, the other must be true also. Okay. Second note, number 2. If the converse is true, so if it happens to be that both the original statement and the converse is true, they call that a biconditional statement. Is a biconditional statement. And I'm going to underline that so we see that phrase as kind of like a definition. Okay. Okay, so let me give an example of a biconditional statement. If one of two numbers is 0, so I have two numbers and I know one of them is 0, then the product of the numbers is 0. That's, of course, knowing that you understand what the word product is. Product meaning a multiplication, which if you know that you multiply by 0, you get 0. So clearly this statement is a true conditional statement, okay? The converse of this is to swap the order with which we write it in. Oops, let me write this in red. So the converse would be if the product of the numbers is 0, then one of the numbers is 0. And there you go. That statement is true also. Knowing that you had a product of 0 pop out, one of the numbers had to be 0 for that to happen. Okay, so the converse is true. That's a biconditional statement. And often in math, when you make a biconditional statement, you can use this phrase called if and only if. Meaning it goes both ways. So if one of two numbers is 0, or you should actually drop the if at the beginning. So one of two numbers is 0 if and only if the product of the numbers is 0. That is a way of phrasing it strictly as a biconditional, meaning one being true goes the other way. Both ways work, okay, of the if-then format. Okay, so there are a couple of phrases they use that I just want to make you familiar with, but it's more about how they apply to arguments and validity that I want to kind of focus on here. Okay, so the first one is the law of detachment. Law of detachment. And as I write it, and then you get to see an example of it, I think you'll understand what I mean, that it's not so important that we know this phrase, law of detachment, but we know what happens under the law of detachment. And here's what happens. Okay, so the premises are, number one, you start with a conditional. If P, then Q. Great. Oops. Number two is that P happens. So P is going to occur, whatever P is. So our conclusion automatically is going to follow from the if-then statement. We conclude that Q happens. Okay, that is the law of detachment. So let me give you an example so you can see that it actually very clearly follows the if-then format. If Jan, oh, sorry, let me write that this is a premise first. Premises. So one, if Jan applies for the job, she will be hired. Okay. Jan applies for the job. Or let's say applied for the job. We'll say it in past tense. So we conclude that Jan gets hired. Or will get hired. Sorry, letting it catch up with me. There we go. Jan will get hired. There we go. Okay, so we can easily prove the validity of this argument with a Venn diagram here, starting with the very first statement, if P, then Q. Okay, so remember, we're doing a subset notation. Okay, so the premise of Jan applying for the job. So we'll let A be Jan applies. Okay. And then the other set, I'll go ahead, J. Jan gets job. Okay. So A is going to be inside of J. All right. Now, what we found out was Jan did in fact apply for the job. So this event occurred. So they put the little dot inside the circle to indicate that that event happened. We've existed inside this event. Jan applied for the job. Therefore, it follows that Jan gets hired or gets the job. Okay. So we conclude that this is a valid argument. Okay. Because it clearly is going to follow from the subset model that the job is going to happen. So this is a valid argument. All right. Then we have the law of contraposition. The law of contraposition starts with the premises. If P, then Q. But now we're going to use the contrapositive argument. So Q doesn't happen. And we will conclude that P won't happen. All right, let's look at an example of that. If a trip is over 300 miles, sorry, let the computer catch up there. Trip is over 300 miles, then the camper will run out of fuel. All right. Sorry. Fix that. That is an of, and that is the word out. Run out of fuel. Sorry, let's make it look like a nice word. There we go. Run out of fuel. Okay, sorry, that's the premise. Wow, I forgot to put premise. These are premises. Okay, and it's the first one. Second premise, the camper does not run out of fuel. Sorry, it's got to catch up with me again. Doesn't run out of fuel. So the conclusion will be the trip wasn't over 100 miles. Now, again, this is, I'm sorry, over 300 miles. This is the subset argument that we're going to set up again. And as I showed earlier, we'll end up outside of them. So it will follow and make sense. It'll be a valid argument. Okay, so let's go ahead and say T is for trip over 300 miles. Okay, and then let's say F is for camper running out of fuel. Or yeah, run out of fuel. Run out of fuel. Okay. So what we're saying is the trip of 300 miles happening is going to cause, or sorry, is going to give us the conclusion that we run out of fuel. Okay. But our second statement says the camper didn't run out of fuel. So we are outside of the green set. Therefore, we would conclude that they also didn't have a trip over 300 miles because that's within the green set. So if we're outside the green set, there's no way we can get there. So this would be a valid argument. Okay, so let's try one more to kind of put it all together. So let me go ahead and make sure I write premises, which they will definitely do. Give it a second to catch up. There we go. Okay. If a company fails to have an annual inspection, then its license will be terminated. All right. That's the first premise. Second premise, the Samson Company sorry, letting it catch up again. The Samson Company, which I'm going to go ahead and say Samson Co. Their license was terminated. So the question is, does it follow that the Samson Company failed to have the annual inspection? So is the conclusion the Samson Company failed to have the annual inspection? There's a C in there. All right. So let's draw this out. So the first set we have is the basing on the first premise. And here, let me zoom out a little bit so that I can see both. Okay. So a company fails to have, or I'm sorry, company has an annual inspection. Okay, so we'll say A represents annual inspection. Actually, here, oh, look, we'll put AI for annual inspection. Okay. So that'll be what goes here. They have an annual inspection. Okay. Then the other option is, oh, sorry, fails to have an annual inspection. Sorry. Let's put an F in front of there. Fails annual inspection. You know, that just sounds like we're failing to have an annual inspection. All right, fine. I abandoned that. And it's just getting worse and worse every time I try to fix it. So let's just say F is fails to have annual inspection. Trying to write it too small and it doesn't recognize it. There we go. Annual inspection. Okay. It's catching up to me again. Then we'll use T for license will be terminated. Okay. So F is going to be inside of the license terminated category. Okay. Fail to get the inspection, you're going to get your license terminated. That makes sense. Okay. So what we're told is that the Samson Company's license was terminated. And the problem is that's all we're told. And therefore I can draw Samson's Company right here. There's Samson's Company. Let's say that that's where they're at. That would mean then that it's possible that we wouldn't get to conclude that they failed the annual inspection, because there's probably other reasons for a license to be terminated just than to not have the annual inspection. So this is not a valid argument, because I can draw this in a way that makes their conclusion not valid. So it's an invalid argument. And that is how we look at different types of arguments and determine whether or not they're valid using deductive reasoning.